Okay, so today we're going to start a new topic, which is the stress-strain curve, and simultaneously we'll also talk about plasticity. All right, so essentially, what we would like to do is we would like to understand how materials fail. An ultimate test for that is to take a piece of that material and just break it apart, right? And that information will eventually deliver us the stress strain curve. And here I will presently write the engineering stress strain curve, because it turns out that there is another type of stress strain curve that we will eventually talk about. So what we will do is, as I said, we will take a specimen and we'll break it apart. Now the shape of the specimen is important and is typically governed by standards, so that everyone agrees on the test results. Here is a typical test specimen. It has a uniform thickness and has this thinner portion in the middle and thicker portions at the two ends. This is a metallic specimen, this is a polymeric specimen, and this is a rubber specimen that is very easy to stretch. Now, why is the specimen thinner in the inner portion? Well, because what we will eventually do is we will put this specimen in a machine. The machine can be very small or it can be rather large. Eventually in class we will have a demo with a small machine that is capable of exerting only about 100 to 150 newtons, but in the lab we will be able to apply laws of the order of kilonewtons, many kilonewtons actually, and we'll be able to break metallic specimens like this. Now, as we do that, we're going to place the specimen between two grips, so really two grips that hold the specimen like this, and we're going to pull on it. And so when we do that, first of all, we don't want the specimen to slip out of our grip, so we would like to have, for a given limited value of load that we can apply normally to the surface associated with friction, we would like to have a large surface area here so that the overall load is sufficiently large so that the stresses generated in the middle portion are sufficient to break the specimen apart. So now, therefore, what we really want to have is the specimen not slipping, and plus the stresses in a monitored, well-monitored portion to be larger than possibly the portion where we actually hold the specimen, because eventually we are going to monitor a certain portion of the specimen and we'd like fracture to occur there. And that's why the specimen is thinner in the middle portion. That's always the case with tension test specimens. So now, eventually what we're going to do is we are going to apply a load, right, to the specimen, and we are going to break it. And the piece of information that we extract from the test is the load versus elongation. Well, how do we extract the load? Eventually, when you hold the specimen on one end, there is something called a load cell typically that measures the amount of load that you apply. And plus, when you hold the specimen, in this monitored portion, which we're going to call the gauge portion eventually, there will be grips, and these grips will hold the specimen rather tightly, and then when the specimen elongates, the grips will eventually elongate with the specimen, so sort of like that. It will elongate with the specimen so that this amount of elongation will be able to deliver us information about the strain. So we're going to have something called an extensometer that is able to, really it will look like two fingers. You'll see this in eventually the lab experiment, and the two fingers, when they move away from each other, we will be able to measure the amount of strain eventually, and from the load cell, the load information will be extracted, which will help us measure what the stress is. So these are stress strain test uniaxial tension test specimen that we are going to employ these two, and perhaps eventually this one as well in future parts of the course. So these are typical specimens that people use. So let me draw that specimen over here. So we have a rectangular cross section of uniform thickness. Okay. We apply a certain load that we measure with the load cell, and the portion on which we will monitor the elongation of the specimen is called the gauge portion, and the initial length of this gauge portion, let's call it Li. Now, of course, there is a cross-sectional area here. Let us zoom into that portion. So that's the cross-sectional area of the specimen. Let's call that AI, the initial cross-sectional area. So this is what we're going to use in the experiment. Not all specimens have to look like this. The specimen can have a circular cross-section, but in all cases the middle portion is thinner, and you're going to monitor, one monitors the elongation in the middle portion and associates that with the strain. So let's say, or of that shape, or perhaps of some other special shape as well. So now Li, as we said, it's the gauge length. It is the initial or undeformed length of the specimen associated with the gauge portion. AI is the initial area of the cross-section, both of them having to do with the undeformed shape. And this is the information that we extract from the geometry of the specimen. So before we do the test, we have access to this information. Then, with the extensometer, we measure the length change. And from the load cell, we measure the applied load. Okay. So, well, that's our piece of information. That's what comes from the measurement, right? And however, what we need is stress and strain, okay? Because the load depends on, for a given amount of extension, how large the cross-section is, and the elongation depends on the initial length, but stress and strain, eventually, the relationship between stress and strain is something that is eventually intrinsic to the material behavior, whereas load versus elongation curve depends on both the material behavior and the geometry of the specimen. So what we would like to extract is something that is intrinsic to the material behavior. So what we need is the stress-strain curve. And so we're going to plot stress, which is load over the initial area, versus strain, which is change in length divided by the initial length. So we only have one stress and one strain. We understand that that's in the direction of loading. So this is obviously the stress, and that is the strain. But let me append the adjective engineering, and we're going to see why we need to distinguish this definition of stress and strain as being the engineering stress and strain very soon. Okay, so that's essentially what we would like to do. So we do the test, right? You take your specimen. Let me take the soft specimen because everything is so visible. You apply a certain load, the specimen elongates, you measure the length change versus the applied load, and eventually you post-process that information. The cross-sectional area doesn't change, the initial length is well defined. The cross-sectional area will change, but our definition of engineering stress takes as the area as the initial undeformed area. So we just post-process that information that is coming from the extensometer and the load cell, and we eventually have stress versus strain information, and that's now what we would like to plot. Okay, so let's do that, right? So we generate a plot of strain versus stress. And now I'm going to draw a curve that is highly idealized, and we'll be able to discuss this curve in detail in the upcoming portions of this topic, right? But let me first draw a idealized curve. So first we observe a almost linear, ideally perfect linear relation between stress and strain, and then again ideally a distinct deviation from that linear relation. And it turns out that when we plot engineering stress versus strain, this curve not always, but again ideally, makes a peak at a certain point, and then it starts decreasing, and at some point the curve stops because the material will break apart. Okay, so this is our prototypical engineering stress strain curve. Now, to understand what is happening here, what I will do is I will try to monitor what happens in the gauge portion of the specimen. Now remember, the specimen looks like this. Here I'm drawing now a specimen with a circular cross-section. What I will be doing now is I will take this portion and only plot the gauge portion. So this is what we start with. So here the gauge portion is, let me exaggerate, looks like this. Then we come to a certain point, okay, there. Now again exaggerating, the cross-section is slightly smaller perhaps, and the specimen is slightly longer perhaps because we are pulling, so it will extend, and assuming the Poisson ratio is positive, which usually is for these types of specimens, then the cross-section is going to get thinner. So then as we pull more, what we observe is that the specimen keeps getting thinner, okay, although I may not be able to perfectly depict it that way. Let's again exaggerate. It does get thinner until it gets to this portion where the stress-strain curve, what's special about it is that the tangent to the stress-strain curve is horizontal. And at this point, what we observe and what you shall be seeing very clearly in the experiment is that now it's the cross-section is yet thinner because deformation is larger, and it is longer. Okay. And at that portion, a tiny dent starts to form in the gauge portion of the specimen, not necessarily in the middle, somewhere across the gauge portion. Now that's like very much like the neck connecting the body to the head, right? So it is like a neck, and it's called actually necking. Okay, so the specimen necks somewhere along the gauge portion. Now, this, it turns out, is not, it has to do with the way the material behaves, but connected to that, it is a structural phenomenon. It is an instability. It is, in some sense, not exactly because it's an instability, in some sense like buckling, if you like. Again, not exactly, I'm just trying to make an analogy. But eventually, after that point, this neck will never return back. You will never see the specimen being perfectly cylindrical again. What will happen instead is that this neck will keep growing, and such that at that point, when the specimen is about to break, this neck has extended all the way into the cross section, and it becomes thin enough to break the specimen apart. So this is where you have fracture. Okay. All right. So let's mark certain critical portions on this stress-strain curve. So first of all, we have the distinct deviation from the linear relation between stress and strain. This is what we have denoted earlier to be the yield strength of the material. And here, let's call this epsilon 0. This is the strain at which yielding occurs. Then there is the portion, the point where the material reaches the maximum stress. Let's call that sigma u. U is here standing for ultimate. So that is the ultimate strength of the material, sigma u. Okay, that's the ultimate strength. And the corresponding strain, let's call epsilon u. And this point here, it is going to be denoted with sigma f, f for fracture, and the corresponding strain, let's call it epsilon f. Okay. So this is your prototypical stress-strain curve. This is what you observe for a broad range of metals in particular. The elastic portion followed by a deviation from linearity. That's how we know it's elastic, right? There's a linear relationship between stress and strain. Deviation from that relation starts indicating the onset of plasticity, and then we have the ultimate, the largest stress that we observe in the along the stress-strain curve, and eventually the material breaks apart. What distinguishes physically that ultimate point is the onset of necking in the gauge portion, somewhere along the gauge portion of the specimen. Okay, so this is the ideal, let's say, the ideal stress-strain curve that we are going to refer to once in a while. And again, which stress and strain? It's the engineering stress and strain. Now at this point, what you may want to think about is, if this is the relation between engineering stress and strain, well, how does the relation between load versus displacement look? In fact, perhaps I should have asked the question the other way around. If I have the information for load from the load cell and elongation from the extensometer, the question is, how would the engineering stress-strain curve look? Now, what you should remember is the stress is simply the load divided by the initial undeformed cross-section area, which doesn't change throughout the experiment, and the strain is the elongation divided by the initial length of the gauge portion, And therefore, because those scaling factors, the area and the initial length respectively, they don't change with deformation. They're just scaling factors. And therefore, the curve for load versus displacement is going to look exactly like the curve for stress and strain, or vice versa. Once I have the curve for load versus displacement, again, highly idealized, then I can extract the curve for stress versus strain, and the two are going to look exactly the same. Why? Because eventually the way I extract the stress is by dividing this load by a constant factor, and the way I extract the strain is by dividing this by the initial length of the gauge portion. So the shape of the curve might slightly change because of these scaling factors. It might get thinner, it might get longer, etc. But the overall trend and overall, let me say, characteristics is not going to change. So load versus displacement is the same. Apart from the scaling factors, it's the same as stress versus strain curve. Okay, so this is what we have so far, the ideal engineering stress strain curve.